So what are we going to talk about? We're going to look at a setup where we want to remote attest a system where the disk, the entire root disk of the system is a LUKS encrypted root partition. So kind of something like that. And we're going to use TPMs and an attestation server to actually do the attestation. So the goal is that we don't trust the system until it's actually attested. And only when it is attested, we release the key that it's going to use to get the disk. So the first step is that when you're booting the system, in the initRD, in the UKI, there will be an agent. It will go and ask a quote of the PCR values to the TPM, a signed quote, and it will send that quote to the attestation server. The attestation server will look at it, verify that it's actually correct, the right PCR values, it has the right measurements, the system is in the expected state. And if it's good, if everything is okay, then it will release a key to the system that the system will be able to use to unlock the root disk partition. And then resume booting, normally getting access to the system. So to get all of this working, we'll need to look at three main parts. The first one is how are we going to set up things on the disk? The first thing is that when you're booting system, generally systems are not encrypted by default, and you don't really want to do that because you want to have a different key for different systems, etc. You don't want to reuse keys, reuse encrypted disks. So the first step is we're going to look at things, how we do integrity on the system before it is actually encrypted. Then there will be some part about the TPM. How do we actually, what do we measure? How do we pre-calculate the PCR values? How do we do all of those things? And finally, we'll look at the attestation server. So how do we actually verify that the system that is remotely running is actually the one running the stuff that we really want to have and not just some random things? And so for the first part, I'll leave it to Pragyan for the UKI and Composefs part.
Thank you, Timothy. So let's take a look at how we can verify the integrity of the root file system using Composefs. First of all, what exactly is Composefs? So it's a file system, but it's not an in-kernel file system. It's a combination of three kernel technologies, mainly overlayfs, EuroFS, and fs-verity. Overlayfs, I mean, you guys must all be familiar with overlayfs. EuroFS is just another read-only file system, and fs-verity is like dm-verity, but it works on files, and it's also optional. Okay, let's go deep into fs-verity and what it actually does. So it is a way to ensure the integrity of a particular file and its contents. So it only does files and its contents. It doesn't actually do anything with directories or metadata. And how it actually works within the kernel is the kernel, when you enable fs-verity on a particular file, the kernel will create a Merkle tree for that file and give you at the end a hash for that file. So basically, you have compressed that entire file to a single hash. So files will be immutable when you enable fs-verity on those. So they'll be read-only. And for verification, you don't usually have to rehash the entire file if you only want to verify just a part of it. Since the Merkle tree that's created is using page size or any block size that you might give to the kernel, whenever read happens on a particular part of the file, only that part will be hashed, and a kernel will verify that. Okay, what is EuroFS? Again, it's just a read-only file system. We use it to store the metadata for the file system and the layout for directories, files, where they're supposed to be, how they're supposed to be, and their relationship to each other. And at mount time, we basically mount this, and we basically mount the EuroFS image, and the kernel composes a file system tree with the mount options we give it. Right, so let's take a look at what it exactly is and what it does. So this is the layout of Composefs repository on disk. We have a directory, Composefs or whatever. In it, we have an images directory, which basically contains the EuroFS image. And you can see that dotted line over there, which basically means that this EuroFS image is stored in objects directory. Objects directory is like a content addressable store. That's where we store all our files that have fs-verity enabled on. That lock you see, that basically means that all the files have fs-verity enabled. All right, so this is what the ERFS actually looks like. It's nothing but just the file system tree, and it stores all the metadata and stuff for the files. Right, so while mounting, we mount this as an overlay FS with ERFS as the upper layer, and for the data layer, what we do is we point it to the objects directory so that we can make sure to get the data from somewhere. Since the ERFS does not contain data, it only has metadata for files. Right, so we use overlay.redirect extended attribute to make sure that the kernel knows where to get the data for the file. So let's say over there we have bash, and we're like, okay, so just redirect it to this particular file in the objects directory, which contains the data for the for bash, basically. Now, here comes the interesting bit. We have the fs-verity digest in trusted overlay metacopy extended attribute in the ERFS itself. So the kernel knows whenever it loads, let's say, any file, it will actually verify the fs-verity hash of that file before it opens it. Okay, so that's our root partition, which is fine. When we mount the ERFS image, by the name, you can see it's a read-only file system. So your entire file system will be read-only. So what do we do with the state? What we have right now is etc and var are actually writable, but everything else is read-only. That's what we have right now. Now let's look at how we can build a fully verified boot chain out of this. So we saw how we can preserve the integrity of the root file system, but like how do we make sure that the entire boot chain is verifiable? So we have our root partition, and what we do is we build a UKI, unified kernel image. We put the kernel, init.rd, and everything else that's required for booting into a single portable executable binary, and we boot through that. So in the kernel command line in the UKI, we have a Composefs hash, which is basically the fs-verity hash of the ERFS image. And what we basically do is we have some code in the init.ramfs that looks at this particular hash, make sure that this is the one that's supposed to be mounted as the root file system, and make sure that the fs-verity of this ERFS is actually equal to the hash that we have in the init.ramfs. In the kernel command line. Yeah, so we can sign the UKI for secure boot. We can do the same thing for shim, which is optional. We can sign systemd boot for secure boot, and we can put all of it in the ESP. And your keys can be in the firmware, so everything here would be signed. And at the end, like I already said, that Composefs hash is equal to the fs-verity of the ERFS file. So what does it actually mean to have this fs-verity of this ERFS file? We have our entire root file system in this, the metadata of the entire root file system in this ERFS image. So basically what we have done here is we have compressed the entire root file system to that hash over there, that A30021 stuff. Okay, cool, that's fine, but how do we actually integrate this with bootc? So bootc is a tool, if you were here in the previous talk, you would know that it's just, it just takes an OCI image, OCI container image, and it makes it bootable. So it extracts the OCI image on the, basically on a disk and makes it bootable, so make sure it's not running as a container. What actually matters for remote attestation is that we have support for UKIs and UKI add-ons, which we do. We need support for systemd boot, which is in progress, and we need support for ignition modules in init.ramfs. Okay, the other component in remote attestations are TPMs and PCRs, which I will hand off to Vitaly.
Thank you, Pragyan. So as you just told us, we are building a system which can later be verified, like the boot chain can verify it. But you can actually now go and verify it. And for that, the answer how you usually do it is by using a remote attestation server. And you need some evidence from the guest, and this usually comes from, among other things, from the TPM. So what are the TPMs? TPMs are like amazing devices. They can store keys securely and do some operations on them. What's important for the measured boot case is that they have platform configuration registers where stuff can be measured. Basically, each next value depends on the previous value. So there is just like if you think that the hash function cannot be reversed, then there is just one sequence of events which could lead to the observed PCR value. Then the good thing about TPM is that it can give you assigned PCR code. Basically, that the observed values of the PCR register on the system are this, and they're like signed by a key from the TPM. And it can also like evaluate policies like limit access to certain objects like keys when the observed state of the PCR is like this. So yeah, so there's a lot about good things about PCR, and the only bad thing is that that's just a few people in the world who understand how they actually work, and I'm not sure I'm part of this group, but I linked a few presentations which I think are useful, right? It's like Matthew Garrett, like a few years ago, talking about like TPMs in general, then Leonard this year's FOSDEM, I think, about how we use TPMs in System D, and then two presentations from James Bottomley on our challenges on how we use TPMs from the kernel. So if you're interested in TPM, I highly recommend you to look at this. All right, so we are going to do a measured boot, and we are going to observe some PCR. So like, how do they normally look? Normally, you will get something like that. This is like SHA 256. 512 would be twice as long. So the question is, like, which of these numbers are important for us, and how do we actually know what should be there, right? These are just some hashes. So let's take a look at how the system which we described is going to boot. So we have like certain PCRs, and I'm only going to talk about the PCRs which matter for which we believe is matter for our case. There are like other ones which we don't use, and again, like if you go to previous like presentations, you will find some information about these PCRs. So it all starts with the firmware, which is going to measure like the firmware config, optional ROMs, optional ROM configs, and the first like, thank you, for PCRs. And then it will measure the certificate which is used to sign that the first stage bootloader, like normally shim to like PCR 7. Then shim is going to boot. Its authenticate is going to be measured to like PCR 4 first. Then it's going to again measure the next object in the boot chain to PCR 7. And also there is a thing called machine owner's key, where you can extend the keys which you are using for your system secure boot. If you are, for example, like a hardware system where you can hardly modify your secure boot DB, you can issue a machine owner's key, and then shim is going to measure it to PCR 14. Then, for example, if we have secure boot, again, its authenticate goes to PCR 4, the certificate of the next boot target goes to PCR 7. More or less same happens to the UKI. The only thing which changes is that we also have the magic PCR 11, which has all the sections of the UKI as well there. And then we can now extend UKIs with various add-ons. We have command line add-ons. And command line add-ons, they are PE binaries, actually. So we measure them as PE binaries to like PCR 4 and PCR 7. And also like there is a PCR 12 with a modified kernel command line. And then we have system extensions and configuration extensions, which are not PE binaries, which are basically like file systems. But good thing that we also measure them for like into PCR 12 and 13. And I guess PCR 12 also gets credentials measured, if I'm not mistaken. So the good thing about all this, that what you see on the left, the ESP, like all these objects are now contained in the OCI container, right? You don't need anything else. So if you know the environment where this system is going to boot, and you know the OCI container, you can predict basically the values of these PCRs before you even boot on this environment. The question is like, which of these are important for us? And like, quickly speaking, like, first 4 PCRs is if you want to log to the environment where this is going to run. You will unlikely to move this system to some other, say, like cloud instance and get the same PCR values. PCR 4 is pretty basic. If you need to be sure that all the P binaries which you had, like shim and sdboot, had like certain hashes, then you will log to these. PCR 7 is interesting because it only works well with when secure boot is enabled. Then you will have all the certificates which were used in the chain. You will also have shims like SBAT level. It's like a generation-based revocation mechanism which was invented when we realized that revoking something in the secure boot chain by revoking the certificate is too expensive. So we came up with a simple mechanism which is like SBAT, and it's kind of also like important if you consider revocations. PCR 11 is somewhat optional if you already have PCR 4, but to me it has one nice feature. There is a thing called PCR phase, so you can actually log to the specific boot stage. So for example, you can attest that the system is now in the initramfs stage and not like past the initramfs stage. Then extensions, if you're interested that you only have certain extensions and don't have more extensions, for example, if you sign them all with the same key, then you will need to check like PCR 12, PCR 13, and mock may also be like important because this key is normally going to be trusted by kernel later. So one more thing I wanted to talk about is how it all relates to confidential computing and it all matters, because these confidential compute instances become a thing, right? All hyperscalers, for example, already have some offering for confidential virtual machines. And on confidential virtual machines, you will also see a thing which is called like launch digest, which basically describes the state of the VM when it was created. It's like the state of the memory and the CPU registers. And the question you may have is, how does it relate to VTPM? Do we still need TPM or not? Thing is that it only covers the firmware, the launch digest, right? All the artifacts which you load later from persistent storage are not in the launch digest. So for that, you need to use something else to verify them. And TPM is normally the answer, although you need to see how the particular platform implements it, because it may or may not be confidential to your taste. Let me put it this way, right? Because like all clouds, as far as I know, implemented it differently, and they all don't quite like each other and say that the other implementation is not as good as theirs. Depends on what you trust. All right, so that's all about the TPMs I wanted to tell you, and now I'll hand it over to Timothy, who is going to put it all together and show how it all going to work.
Thanks, Vitaly. So yeah, now that we have the boot chain, the fully trusted boot chain, that we can verify that we're booting something that we want and booting the right version of the operating system, we know which PCR values, how they are used, how we can predict them. We're going to use that for remote attestation. And so for remote attestation itself, we're going to use something called Trustee. It's a project that comes from the Confidential Containers project. It's a CNCF sandbox project, and it provides essentially two main services. The first one is the attestation service. It's a component that will verify that when you give it a set of PCR quotes signed in hardware reference value when using confidential computing, it will verify that everything is correct and actually signed by the right keys. And then it will pass that information to the KBS, the key broker service, which will hand over back some secrets, some key values stored secrets to the client that requested the attestation. And all of this is configured via what is called REGO policy. It's a policy language that defines where you can define what PCR value you want to check, how, etc., against which values. And the last piece that we need here in this setup is something to encrypt the disk on first boot. And in our use case, we're going to do that via ignition. So on core systems, we can automate part of the partitioning of the system, part of the setup of the system using ignition. And one thing that is that ignition is capable of is re-encrypting the root disk using LUX. And so it's going to do that on first boot. So on first boot, it will read the content of the disk. In the initRD, while running in initRD, so the system is not booted yet. It will save it back in RAM, set up the LUX device, set up the right key, do the attestation, and then write back the content on the disk. And then on later boot, well, we do the same process. We don't re-encrypt the disk, but like we do the attestation again, and we unlock the disk, and we resume booting. All right, so let's look at how all of this actually works in practice, so that we know we're not cheating. It actually works. We are going to create first what we call a sealed bootable container image. So we're going to put a signed UKI, secure boot signed UKI, into a container image. Then we'll pre-compute the PCR value. So we're not going to do the whole set of PCR value, but we'll look at 2 PCR values, and we're going to pre-compute those from the container image. Then we'll set up those values inside of a trustee server for attestation. And then finally, we'll boot up a node, and it will remote attest itself with the server and encrypt the disk on first boot. And finally, we'll update the system to a new version, which will have different PCR values. And we'll set up those values again in the attestation server, reboot the node, and we'll verify that everything boots correctly. So let's do that. All right, is this working? No. Yeah, it is. So first, we have here kind of a simplified Containerfile that we are using to build our sealed container image. So we start from the bootc image, bootable container image, and we're going to pass it as an argument the Composefs fs-verity hash, the hash of the actual final role system that we're going to boot. As it's a multi-stage build, we can install a few tools in there that we need to build the UKI, and we're going to build this one, sign it, pass it the Composefs hash, and finally put the UKI in /boot, a special place where it is not taken into account when computing the hash again. And so that's essentially what this is doing. We're doing a regular container build, getting the Composefs hash, building the UKI, installing the tool, building the UKI, and putting everything into a final container image. Yes. Okay. So yeah, installing the tools. We don't need to have the UKI tools like in your system. You can install them dynamically because here is a multi-stage container build. UKI file will generate us all the PCR phases for system D. Here we sign the UKI, and we're also signing a UKI add-on. Here we're signing a UKI add-on for ignition because it needs a specific kernel command line addition on first boot. And finally, we copy the UKI into /boot. Okay, all right, so now we have a sealed container image with a signed UKI. And what we're going to do with that is we're going to upload it. First, we'll check that actually we do have the UKI in the container image, so it's over there with the ignition kernel command line add-on as an extra UKI add-on. And we're going to copy it into a remote registry for delivery. Nothing special here, it's a container image. We're pushing it. As soon as it is pushed, we'll then create a disk image out of it. So the bootable containers, the idea is that you have everything inside of the container, but we're not actually booting the container image. We're extracting the container image, the content on the disk, and that's the setup that we're booting. So to do that, we actually use a few different tools. Here is a set of wrappers around bootc install to filesystem, which is capable of like extracting things and setting up a disk image for you and writing the content of the container in the right place. So now, in parallel, while this happens, we're going to pre-calculate the PCR values that we're going to get when we're booting this container image. The first one that we're going to do is PCR4, so PCR7, sorry. Yeah, PCR7, PCR7. So we could theoretically compute it from the container image, but it's the one that's never going to change because we're always going to use the same key to do the signing. So here we computed it from a set of static files that makes it a little bit easier. But ideally in the future, we would directly compute it from the container image. The second one is PCR4. PCR4, we need shim, we need systemd-boot, the UKI to compute this, and the UKI add-ons. And so here, this one, we're actually computing it from the container image. So we're not using something else, like you can directly pass it, you run the tool in the container image to get the right values. And you get here the PCR values, and the other one here on the bottom are shim, systemd-boot, the UKI, and the add-on. So I'm copying those values, and then I'm going to go to the attestation server. So the attestation server, it's a set of containers running the trustee components. And one of those containers is the actual key broker service, which is kind of like the central part that we're going to talk to with those tools. We have here a regal policy where we're going to tell the attestation server to verify the PCR4 and the PCR7 when it is going to do the remote attestation. So first we set up that actual policy. We tell the trustee server to use that policy for the attestation process. And then we are going to set up a secret. So here's just a random value that we are going to set in the trustee server, in the key value part, so that the actual node can fetch it and encrypt the root disk with it. So here we're setting up the secret, and then we're setting up the two reference value that we want for PCR4 and for PCR7. And we're telling that to the attestation server. All right, so our disk image is now ready, and we're going to boot a final system, the final system that we're going to attest. So here, this is a regular libvirt VM on my system with a set of secure boot keys set up in the firmware. And this is the systemd-boot interface, and we're booting a specific version. So it's booting a UKI. And what will happen is, the first thing that will happen, it will fetch its bit of an ignition config that tells it what to actually do on the system. And the first bit that it will do is it will notice that it will have to re-encrypt the root disk, re-encrypt the content of the root disk. So it will read the entire content of the root disk into memory. It's capable of doing that safely because everything is here fs-verity verified. Again, like we have the Composefs hash, and we can do that safely to read the content into memory. So we know that we're reading the right files. Once he has done that, he can set up he can wipe the disk and set up the LUKS encryption for the root, for the partition. And then it will remote attest itself to the server and get back a secret. It's here in the middle. Here it's in clear text. And set it up as the key for the LUKS root disk. So once things are encrypted, then we can take back the content from RAM and write it back into the LUKS partition, and then finally resume booting. All right, we have booted the system. So if we look at the /bound point on a Composefs system, here it's referencing the hash of the system that we're booting, the Composefs hash. And we get the same thing from the kernel command line. Here we have the bootctl output. It tells us that we have a measured UKI, we're using TPM support, and secure boot is correctly enabled. So if we look at the system, we have the third partition, which is LUKS partition, and inside like the configuration for LUKS, we have a specific token, and this is where we have the configuration to tell essentially the system when it is booting how it's going to do the actual remote attestation. So if we look at this actual token here, so it's using Clevis, it's a tool that allows you to configure those things, and it's telling the system to go and do remote attestation with the trustee server at this specific URL. and get this specific secret. All right, so now we're doing an update. We're pulling a new container image. We build that one in the background. It's a new version with whatever fixes. And if you look at this bootc status, you have a new version that is now deployed on the system as an update, prepared. And finally, once we're ready to reboot, we tell bootc, hey, let's go and prepare this update for the next boot. And it will write things back. So before we actually reboot, we need to make sure that the PCR values are right in the attestation server. So what we're going to do is we're going to re-pre-compute those PCR values. Here we only do PCR 4 because PCR 7 doesn't change. We're assigning everything with the same keys. So PCR 7 will be the same. We only have to compute PCR 4 again and set it again in the attestation server. Ideally, in a production setup, you would have multiple versions, multiple options for PCR 4, but here we just have the ones we want to have for our demo. And once we're ready, we go and reboot the system. And so the same, we go through the same flow. Here in the system deboot interface, we have those two options, our new version of the system. It's going to boot. It will do the remote attestation, so it's setting up networking so that you go and do the remote attestation to the server. It got the key, and then it resumes booting. And similarly, it uses Composefs, so it knows that it's booting the right version of the system. And here we go. We're now running the new version of the system at the top with the dot. And that's it for us for the demo. We have one last slide. All right. So what are the plans next? So all of this works, but right now it's still in pull request. It's not fully integrated. So it's, the next step is going to be actually merging all of that code into the bootc project. So it's based on several components. The first one is the Rust implementation of the Composefs project, and based on the first version of Composefs, which was written in C. Finally, bootc, which will integrate all of that in the end, which is like what we're showing here. The part that are linked to remote attestation, we're developing that we're creating another organization, the confidential clusters, because the goal then next steps are to integrate all of those processes and all of those setups for booting entire clusters. So we want to integrate that with Kubernetes, how things are done with Kubernetes, because this is where things are interesting when you have control of the entire environment. And yeah, that's it for us. I want to especially thank a few people here that are connected to our team or part of our team, have been working on this. It's definitely not just us three, it's a lot of people working on this. And so I want to mention them quickly, especially Halice, which is here, Benyat, Pradipta, etc., and all of the folks which have been working on with us on all of this. So thank you very much.
We have time for questions, so we already have a question.
Can you explain a little bit more? Like you're copying the root disk onto a Lux thing at boot. Like how do you? What's exactly happening, and how are you establishing the authenticity of what you're doing there? Like because you're mounting the file system and then copying the contents of it, or what's?
Okay, so yeah, when you look at what's on the disk, you indeed have to open the partition on the first boot and read the file system content.
But how do you authenticate that?
So that part you don't. I agree. But the thing is, so I agree, you don't. But then what do you read? You read the files there. So you read the content of the files. Those files are fs-verity.
But you know that the kernel maintainers made very, very clear that they do not consider that an attack surface, right? Like so.
I know.
What is it? Is it XFS or something?
Yeah, it's regular XFS file system. Yeah.
So
the first boot, yeah, you can have to rely on the first boot that you know who's from the beginning. I agree. From this part here.
But I mean, if you do all the attestation chain, verified boot chain, so you basically have a hole in the middle, like.
On the very first boot, yes.
Which then translates to a hole in every further boot as well.
I agree. That's a limit in this design, and it is that if you want, maybe you could do something else. But like right now, you will open the first time you open the partition, you will have to trust the container.
But again, this
well,
translates to every further boot, right? Like if you cannot guarantee the integrity on the first boot, you cannot guarantee it ever, right? Like the moment where you cannot guarantee the integrity, you're lost, right? Like that's how the model works with boot chains.
So yeah, you can. If you have a kernel exploit on first boot, then you can exploit that, yes. But the content you're reading, it's integrity guaranteed. So unless...
Yeah, but by something, you can't guarantee, like, the kernel could be exploited by that point, so it's useless, right? Like, that's how boot chains work, right? Like, every step of the boot chain needs to authenticate the next one, but if you have a major hole in there, like, then the rest of the things...
Yeah, there are other options. Like we could say, okay, the first time we open this, we do something else, or we set up things differently. But yeah,
I thought, don't you check by checking the Composefs hash? Isn't that how you check the integrity on boot?
So that's how we check the file content. But then notice, right, that we don't check the actual like XFS file system integrity. This part we don't check. Yeah. I know, that's the limit of this.
Just use the DDIs and then it will work.
I mean, if second booted on, it's all encrypted, right? So the concern really is the first boot. And the reason you don't ship it wrapped in LUKS at all is because you don't want to have any keys you're shipping until the second boot, until the keys get provisioned. And you're copying everything into memory and back down to disk anyway, you could just wrap the whole thing in dm-verity for the one first boot, copy it into memory, wipe away dm-verity, put LUKS, and put the whole thing down. Seems like a solution.
Yeah, that could be an option, yeah.
So my understanding is on the subsequent boots, your security is based on LUKS guaranteeing integrity. You do know that it doesn't do that, right?
Yes, it's only encryption, but like it makes things harder. I agree that encryption is not integrity, but it's part of the thing. If you want to go the full route and have actually trust in integrity, you need both the encrypt plus the integrity on the LUKS root disk.
You can see that this, like, I mean, it's, yeah.
I know you're not fan of the design. No, it's the compromise we make. Yeah.
So my first question is, why didn't you use dm-verity? And why did you choose this setup instead of using dm-verity? And the second question is, you mentioned measuring the different binaries, shim, grub, and so on, but do you measure their configurations? And for example, the grub config, do you pre-compute the measurements of the grub config, and do you check that too? And I have a third question, which is also, do you do local? Can you do local attestation with sealing the key in the TPM? So 3 questions, sorry.
Okay, so the first question is, why don't we use dm-verity, right?
Yes.
So yeah, this is a common theme here, is the argument we're having before, is the idea is with Composefs is we want to have the flexibility of files with some of the guarantees of the disk images. And the goal here is that most of the time we don't exactly know how big the system is going to be, and depending on what you put in your side of your container images, you don't know exactly things beforehand. So the main problem that is coming with disk images is that you have to reserve space ahead of time. And then when you hit the limits, you have problems. And so that's like where the approach we like with Composefs is that you don't need to reserve space ahead of time. You can write the content on the disk and using a regular file system, and that's how you verify things. The second question is about, you want to go ahead?
Don't use grub. No, like literally, like every line of grub config is measured to what, like PCR 8, what,
yeah.
Right? Like it's a nightmare for attestation. Just don't do that.
You had it in your slides. That's why I was asking.
It was like it is possible to use it there, but we don't use it there. No. So in the example, you could see that there was SD boot and.
Okay, thank you. And my last question was about local attestation. Like, are you planning to support like sealing the the encryption key in the SR key and doing like things with the TPM and policies there?
I mean, yes, in theory, instead of like going every time to the attestation server, you can just seal the key to the TPM. If you consider the TPM device is ultimately trusted, right, and persistent, like that it persists the key, then you can actually, like on the first boot, just seal the key to the TPM, and then on every consequent boot, you don't need to go to the attestation server for decrypting the disk. But if you are like an external user to the system, right, before you connect to it and start using it, you still need to do some sort of remote attestation. You still need to get some guarantee that this system which you are connecting to is actually this system and not something completely different, right? So it just moves this attestation step down, you know, like, so yes, you can avoid doing it in Intram-FS, you can do it from the main system, for example, upon request. Yes, you can do that.
I guess I'd like to respond to what Leonard was talking about earlier with this argument about, you know, if the superblock gets corrupted and everything. And it seems to me as soon as, I understand all the arguments about if you do DM encryption and DM integrity and you protect everything that way, then in theory you should be able to verify in the next boot that there's no evil maid that came in between or whatever. But this idea that if somebody gains control of the system at some point, and then if you do anything less than a factory reset, then you have the same issue, right? Like that writable partition could have been corrupted by the person who was in the fully booted system who had access to the key material. And then for all this talk about, okay, you have your executable stuff here, and over here it's just data, you know, it's safe. We don't have to blow that away. But actually, if your factory reset mechanism does depend on that being blown away because you can't trust the superblock anymore, that's kind of not ideal, right? And I really, really feel like, and maybe this is something that we need to push harder on as, you know, sort of the user space side of these things, the kernel kind of needs to get their act together on this one, right? They need to make reliable file systems that are not ways, even with like secure boot, right? Like you can't load a kernel module unless it's signed, but yeah, sure, if you have a corrupted file system that you mount because you're allowed to mount it because you're root, sure, yeah, you can get into the kernel that way, right? Is that honestly what they're trying to tell us? And I just kind of get sick of hearing this argument because I think eventually they're going to have to fix that. That is a bug, even if they say it's not.
Well, Rust will fix that, right? Kernel for system drivers in Rust. Sorry, yes, so that's all the time we have. Sorry, Leonard. Let's thank the speaker.